measurements of a real-world system or enhancing measurements of the system with a mathematical model. And one algorithm that I've been using is the Kalman filter. But let's talk about the cardiac electrodynamics part. So each cell in the muscle tissue of the heart can be modeled as a small circuit. And there is a difference in the electrical potential between the outside of the cell and the inside of the cell. When one cell changes its membrane potential, it can trigger the release of this calcium ions inside of the cell, which then triggers the change in membrane potential in its neighboring cells, and that causes the heart muscle to contract, causes blood to pump throughout the body, and that's a good thing. But if there is an odd rhythm, if your heartbeat is not regular, if the muscle is not all contracting at once and then releasing at once, you're suffering from something called an arrhythmia. And one particular arrhythmia, ventricular fibrillation, which is specifically an arrhythmia in one of the heart's ventricles, is exceptionally dangerous. It causes around 300,000 deaths per year in the United States alone. So we're also going to talk about dynamical systems. So it's a set of equations that describe how a system changes, and it could be changing as you move through space or as you move through time. In this particular situation, we care about how things move through time, and we care about how they are changing continuously with time. So everything here is going to be differential equation-based modeling. And we're actually looking at just a single cell. We're not looking at the whole heart. We're not looking at like a slab of heart tissue. We're just going to think about a single cell, and at some point in the future, we may be scaling this up into actual tissue. So we're just looking at an ordinary differential equation, the easiest kind to deal with, and we're not going to get our hands dirty with PDEs at this point in time. And because biology makes everything complicated, because every cell is different, we're just going to assume this is a black box model, and we're going to approximate our cell as a circuit, like I mentioned earlier. And we're going to be using this model here, the two-variable Karma model. So we have these two equations that tell us how our two variables that we care about change with time. So we have our variable V, which represents that membrane potential that I mentioned earlier. And that is affected by this large summation term here in the middle, and then an applied current that we see on the left side there, that I over C. I is an applied current being applied from outside of the cell. And then we have a refractory variable that tells us how the cell recovers after that stimulus has happened, right? So we can see typical traces of how these variables look as we propagate them forward through time. As you can see, for the voltage, which is our V variable, these spikes are very steep, which is something that we want. The particular part of the cardiac structure that we're modeling here is what's called a Purkinje fiber, which is located in the ventricles and help with the conduction of the electricity through that part. But we want it to be very steep, so this is good. But because cells are complicated, we're going to talk about it in a slightly simplified way using an analogy that I have heard and that I'd like to share with everyone. Cardiac cells are a lot like a toilet. So, when you're using a toilet, when you're done with it, you apply a stimulus to the toilet and something happens. You turn the handle, the toilet flushes. For us, we apply an external current to the heart cell, and then it is active for a while. That membrane potential changes, it releases its calcium. Then we have to wait a while before we can do it again. You can't just keep flushing the toilet over and over again because the tank hasn't refilled. You have to wait a little while. That's a lot like these cells. They need time to rest and to recover. And if you try to apply that current or that stimulus too often, what you end up getting is you see reduced effect from your repeated stimuli. So in this plot that I have down here in the bottom, in the middle of the left, we can see what the actual behavior should look like for these fibers. That's what the actual action potentials should look like. But if we start applying those stimuli closer and closer together in time, we move down to the bottom one, you can see that odd pattern where we have a long action potential and then a short action potential, and then a long action potential and a short action potential. That period 2 cycling is bad. We don't want our heart to do that. And it's referred to as alternates in cardiac tissue. So now we have a model. We have these 2 equations, they're differential equations. But as I'm sure you're all aware, models are never perfect. We have to make simplifications so that we can write them down, so that we can do analysis on them, so that we can try to solve them. There's a lot of detail that we are not including. Whenever we're talking about gravitation between 2 bodies in space, we never talk about what's the moon doing to it if we're not talking about the moon. But it's still there. So there's a lot of stuff in this model that we're not including, we're not going to talk about. So there's a lot of variables that are affecting our system that our model does not describe. So even if we have the correct starting point for all of our calculations, we can never really guarantee that we're going to actually end up following a real heart cell. And a lot of these, we're going to assume that these errors, these differences between how our model predicts things will behave and how the actual thing behaves, we're going to assume that's a normally distributed random variable with this covariance Q, and Q is just a measure of how much do we trust the model to be telling us what's actually happening. So one way that we can improve what our model says is to actually look at a heart cell and see what it does. So we can take a measurement. But real-world measurements are also never entirely accurate. That's why there's the old adage, measure twice, cut once. You're taking another sample of the same random quantity, essentially. So we can assume these measurements also have some amount of error associated with them, and that these errors are, as before, normally distributed with a covariance matrix R, and R is telling us how much do we trust our measurements. Ideally, we trust our measurements a lot and our model a lot, but this is a way to kind of combine those two. So right now we're going to just go through how the Kalman filter works because it's a little bit complicated. I've tried to simplify it as much as I can. So, we have a linear model. So we have this big matrix A that tells us how our state changes from time j to time j plus 1. And then we have that error that tells us how far apart the real system is from what we predicted, from what our model predicts it should be. And that's this matrix Q, as I mentioned earlier. At any point in time, we can take a measurement of that actual quantity, and that's also going to have that random noise associated with it, this V term, and that V term is also normally distributed with covariance R. So we're assuming that our measurements are always going to be centered around where the actual value is, and their errors are going to be centered around whatever the actual value is. So, we know what A is, because A is what our model is. We know C, which tells us how we're actually going to be measuring our system. And we know what we've actually measured. We know what the voltage is in our case. And we should have some kind of idea of the magnitude of these two uncertainty matrices, Q and R. We might not know exactly what they are, but we can get an idea. What we want is a feedback term that we can add up onto that, our first term up there, that xj plus 1 term, that will give us a better estimate of what we're actually looking at. So, for any point in time, the first thing we need to do is we need to predict what's going to happen next. And the way we do that is we just apply our model, right? So we're just multiplying this vector. So I'll explain my notation a little bit. So we have that x hat j minus 1 given j minus 1. So that is our most recent estimate of what the state of our model is. And then we're going to apply our model to that, and we're going to get the x hat j given j minus 1. So that is our prediction of what should happen next, given what we think already happened. And then we can also keep track of our error covariance, so we can tell how far off are we. We can get an idea of how far off we think we are with this matrix P. So then we can use all of that information we've just calculated in addition to our knowledge of Q and R and C, and we can calculate an optimal gain for our system. And that is optimal if the model happens to actually match the real system, if the noise entering the system is white or uncorrelated, and if we know the covariance is exactly. Those are some big ifs, but we're assuming that they all apply right now. So now that we have our prediction, we're going to take a measurement of the system. We're going to see, all right, this is what the model says we should get. Here's what we actually see. And again, that measurement is not always 100% accurate. So we're going to update those two. We're going to use knowledge of what we predicted should happen versus what we see happening, and try to reconstruct what actually happened. So we construct this feedback term here on the right, this L y minus c xj given j minus 1. That is essentially telling us we're going to be looking in this direction, this yj minus c xj given j minus 1. We're going to move our estimate in that direction, and L is going to tell us about how far we're going to move it. Then we get an estimation error from all of this, and what we're actually doing with our gain L is minimizing the expected value of this error. So that's a lot. Here's a general way to understand it. So we start off with some prior knowledge of the system, something that we already know happened in the past. And we're going to use that as our most recent estimate of what the system is doing. Right? So we have knowledge of what just happened. We're going to use our model to tell us what's going to happen next. Then we're going to take a measurement of what actually happened, and we're going to combine those two to get an estimate of our system, and then we're going to use that as our next most recent knowledge. Does that make sense? Am I explaining that well? Yes.
This might be silly, but is it at all like how the Roombas constantly figure out not to bump into stuff? Is it the same sort of thing, or am I totally off base here? I'm just trying to connect to something I have more experience with.
I don't think so. I'm not 100%.
Sorry about that.
Oh, it's fine. I think that they certainly could use this in a Roomba. I don't know that they do.
My Roomba's not that smart, so it doesn't surprise me.
You need a new Roomba.
So, in general, we can't measure everything that we want to know about a system. That variable v that we had before, we have our two equations down here again. V is pretty easy to measure compared to trying to measure n. N is very difficult to measure. But you can actually kind of get an idea of what the membrane potential is, how the difference in electrical potential between the inside and the outside of the cell is. So we want to be able to take measurements of V, clean those measurements up, and get a better idea of what V actually is. And then maybe we can also use this model to tell us what N could be at any point in time, get an estimate of this unmeasured quantity. But we have a problem. This is not a linear, these are not equations for lines, as I'm sure is probably pretty obvious. These are very nonlinear, and we saw earlier we have those sharp spikes in our model where we go from a very low voltage to a very high voltage in a very short amount of time. And so we have a very nonlinear model. So we need to come up with a couple of ways to fix that, so that this technique that I've been talking about can be applied to this nonlinear model. And for us, as I listed over there, our state variable xj is just the voltage at any time j and this refractory variable at the same time j. And our measurement matrix C is just telling us we're just going to measure the voltage exactly, or with the noise added. So we have a couple options on how we can deal with that whole nonlinear to linear problem. Our first idea is one that's borrowed from control systems engineering. Essentially what we're going to do is we're going to linearize our system, right? So we're going to take, we're going to say, to get from point A in this action potential to point A in the next action potential, we need a matrix that's going to tell us how to go from point A to point A, right? So we're going to be linearizing our system around these period 1 trajectories by computing these analytical Jacobians, and then using these matrices that'll take us from one action potential to the next, we can generate our Kalman gain, as we mentioned earlier. And then we can generate a bunch of these for each of these action potentials. So what we're essentially doing is we are saying to get from this point in an action potential to the same point in the next action potential, we have this matrix A1. And then to get from the next step to the same point in the next action potential, we have A2. And that's what this plot here is illustrating. We're essentially going from the same point in one action potential to the same point in the next one, to the next one, to the next one, as long as we need to, as long as we want to. And each of these matrices is going to have their own gain matrix associated with it, because each of these matrices are going to be different. And we're going to have a bunch of them in each one. So we have a lot of linear algebra going on right now. So that's option number 1. We turn our nonlinear system into an approximation using a linear system. Another option that we have is we could just keep working with the nonlinear system, but we can change how our filter works. So something that you might remember from statistics in university level, if you take a normal distribution, you apply a linear transformation to it, what comes out the other side is still a normal distribution. It might not have the same mean or standard deviation, but it's still normal. If you take a normal distribution and you put it through a nonlinear transformation, what comes out on the other side is probably not normal anymore. It's going to be something weird. So we want to, what this next technique called the unscented Kalman filter does is we take our most recent estimate and we generate a bunch of sample points around it in our state space. Then we take all of these points, we plug all of them into the model individually, and see what happens to them afterwards. So we're moving a bunch of different sample points through our model and seeing what happens on the other side. And that should hopefully give us a better idea of what this posterior distribution is going to look like. And we're still going to approximate it as normal, but we should have a better idea, hopefully, of how that new distribution looks. And we can use this process that's called the unscented transformation, or the unscented transform, to generate estimates for the nonlinear system fully without doing any kind of simplifications on that end. I'm going to be way under on my time.
That's fine.
Oh, I didn't think anyone would complain.
They've had a long day already.
Yeah. So, here's what I've actually done for this problem. We are making the trace plots that we saw before, those high voltage spikes and then they're coming back down. We're just going to generate a bunch of those using Euler's method, so we're propagating this through time in the simplest way that we can, just to get numbers and an even time step of 0.01 milliseconds. And we're going to simulate measurements of the voltage by just adding on computer-generated random noise to the data that we just produced. Then we're going to generate our analytical Jacobians, as we described earlier, from the actual state of a single cycle. So just going from the first cycle to the second cycle, we're just going to use that and assume it's the same from the second to the third, and the third to the fourth, and the fourth to the fifth. Not generally true, but we're making an assumption. Should be close. And then we're using a bunch of MATLAB's built-in functions to actually generate data and to get these simulated measurements. So we're not actually working with real world cardiac data at this point in time, because real world data is always more complicated than you want it to be. We're working with some ideal stuff just to make sure it all works. So, scenario one. We have our two uncertainty matrices that we were talking about earlier. So in this case, we have a very low process noise, which means for us, we really think our model is telling us what we want to know about what's going on here. The model is doing a great job and it's describing the real system fantastically. But our measurements are not very good. So we want to be able to clean that noise up off of the measurement and hopefully be able to reconstruct this unmeasured quantity as well. So what we can see here is on this left plot, these are the voltage spikes, as I was talking about before, and on the right one we have that refractory variable, that inactivation gate. So all the green fuzz around that line represents what we're actually simulating our measurements to be. And if you look, it's kind of hard to see because there's a lot going on there. There's a dashed red line in the middle of the green on this side, and there's that thick black line as well. And there's a bunch of little blue dots on there. So the green fuzz represents what we measured. The red dashed line tells us what the unscented Kalman filter says should have happened. That's our fully nonlinear filter. And then the blue circles represent what our gain scheduled Kalman filter predicts should happen. And then on the right, we have what those are reconstructing. So this is the unmeasured quantity, on the left. On your right, yes, on the right. Sorry. On the right, we have what these filters are predicting versus what was actually happening. So to get a better idea, because I know it's kind of hard to see, we're going to just zoom in on that last cycle for each of these plots. So, we can see some things going on here. First of all, they both do a pretty good job of tracking along the voltage. They do a pretty good job of clearing off all that noise, especially after we give it time for everything to settle down. And that red line and those blue dots are both following along the center of the green, which is what we want to happen. But on the right side, we see something different happening. Our unscented Kalman filter, the fully nonlinear one, seems to be having a really hard time following or reconstructing that quantity in general. We have that big chunk taken out of it where it seems to think that it's constant for a while and then it shoots back up. And then we have, it kind of follows along the underside. And that's kind of typical for what we see in these scenarios with the unscented Kalman filter, as we'll see in just a second. So we're going to look at one more scenario, and then we're going to go to some big results, big picture stuff. So, scenario number 2. We think our model is terrible, but we think our measurements are pretty good. What happens? So you can see here, all that green fuzz that was going on around our measured quantity, our voltage here on the left, that's pretty much gone, and it's all within, it's all very small magnitude. But you can see that there's some extended transience period, especially if you look, there's that little blue spike that happens above the second action potential that tells us that the linear filter is predicting it coming back up again at that point and then going down the way it expects to. So there's an extended transience period here. And you can see that a nonlinear filter did a terrible job of trying to reconstruct that second variable. You can see that dashed red line along the bottom of the plot, nowhere near the actual result, or nowhere near the actual values. Now if we just zoom in on that last cycle again, we can see pretty similar stuff going on. It's kind of hard to tell on this left plot, but if you look at our values that we have here for our error norms, the linear filter actually did a pretty bad job. It's not terrible. You can kind of see it in there small, and I apologize for that. the little dots are actually kind of falling off below where the action potential is on the left. And on the right side, you can see, again, the nonlinear filter did a terrible job. Nowhere near the actual values that we're looking for. And even the linear one had a harder time trying to reconstruct this, and it's not following that line very clearly, so it's not having an easy time of reconstructing everything. So, I did a bunch of trials. Here's some data. I'm just going to narrate through it real quick. In general, it looks like the unscented Kalman filter performs better than the gain scheduled Kalman filter if we have low measurement noise. So if we trust our measurements a lot, it does a pretty good job. But it does, across the board pretty much, do a terrible job of trying to reconstruct that unmeasured quantity. And it's not entirely clear why that is yet. We're still looking into it. The linear filter, that gain scheduled Kalman filter, really doesn't do well if we have a high process noise relative to our measurement noise, but it does an alright job of reconstructing that unmeasured variable in most cases. Restating some of the things I just said, the nonlinear filter does a really bad job of trying to generate unmeasured information from measured quantities, but it's good at following along with those measurements and clearing off the noise. And the linear one does better when we think our model is more accurate than the measurements that we're taking. We've done some additional tests as well. All of these were when the impulses that were coming into the system were at 800 milliseconds apart. We've done some additional testing at 500 milliseconds. So those nonlinear portions become closer and closer together. And the linear one just starts to become unstable and completely untrustworthy in those scenarios. So we're still working through some of that as well. So here's what I'm going to be doing with all this next. So the project I'm working on currently is to be able to reconstruct this electrical information from measuring the actual movement of the heart tissue. So we can take it like an MRI of the heart tissue, we can see the walls of the heart moving, and then we can use that to try to reconstruct what the electrical current that passed through that area was. Because we have a lot of ideas about what it should do, but it's really hard to take measurements of three-dimensional electrical activity. Eventually, we'd like to maybe look at a fully time-varying linear Kalman filter. So instead of doing cycle to cycle and doing our filter on that, do time step to time step on that Euler time step scale to try and see what happens there. And we're going to look at some other comparison means and try to space out some stuff. And eventually work with real-world data. And that is everything. Thank you, everybody.
Does anybody have any questions for Christopher? No? Oh, yeah.
I do. I'm not gonna lie to you.
Yeah.
It is too long ago in my past. I don't remember all the things you're
understand.
talking about by any stretch of the imagination. So my questions are gonna be more from an end of a high school teacher sending kids off to college to
Absolutely.
do things that we have no idea.
Happy to answer those questions too.
Good. Notation wise.
Yes.
Like that's a huge thing. Like kids in high school do not enjoy notation. That is one of the
Right.
things I really kind of hammer home. When did you start thinking that you were learning, whether it was learning on your own or if you remember someone specifically teaching you about the notations in that slide?
In which
In
one?
your slides, in all of them.
Okay.
Like, like when you get into, when did you feel comfortable reading notation?
I think that I'll say one of the biggest changes for me was moving from, in Calculus 1, the first time I took it, because I took it like 3 times, because my undergraduate experience was weird. But one of the biggest changes for me was switching over from trying to do everything with prime notation to doing everything with the differential notation. I find that it makes it way more understandable. It kind of explains what's actually going on a bit better to me, as far as I could tell. In general, when did I start picking up on notation? It's kind of been a gradual thing. I think one of the bigger classes that I started figuring it out in was probably differential equations. That was when it first started to, it was kind of one of those things where it was get on the boat now or it's leaving without you. I was a computer science major at the time though, so I didn't feel the need to get on the boat, but I got on the boat anyway.
Anybody else? No?
I have some thoughts about Roomba. I'll run these by you.
Okay.
Since that was right. With this DNOK analogy, if we have to make this like a vacuum cleaner. I've never had Roomba, so let's say
Neither have I.
you've had Roomba and for some reason you're really way too invested in its internal workings, you care too much about what's happening inside it. Maybe it has a motor that creates suction, it runs a pump or something. So maybe your project is like, if let's say you use a motor speed loop for the pump, you're trying to estimate the suction from the motor speed and have it do the suction correctly. I don't know. So let's say there's a sensor on board that tells you how fast the pump will go, and then that's connected somehow to the suction. There's like a mathematical model for
Right.
those two. So you have the model and you have one of the measurements, but you're trying to get another measurement, maybe you can, an estimate of the suction from the motor speed, something like that, vice versa.
Yeah, that makes sense. I think the question was about specifically how the Roomba was moving around and managing to not bump into like the wall over and over again.
That was a very generous
Yeah.
interpretation. Thanks for making me feel smarter. So.
I didn't know about that yet.
It makes perfect sense for what we're talking about
Okay.
here. Any other questions?
Okay, so before I wrap this up with Chris, let me just bring up the fact that having been a CS major and then doing the math, does anybody have any students that are interested in computer science that they know of that are super geared towards that area of study that you know of? I see a couple heads nodding. We can raise our hands like our students. Anybody, can you think of anybody that's geared towards that? No, Sam?
I had a couple of students that taught computer science last year, just ended the year. So, there was a couple that kind of really rose up in the ranks as far as figuring things out. And one of them in particular said that's what they want to do, that's what she wants to do.
Okay.
Yeah.
And so that's why I really think talks like this are great. It's not necessarily that you're gonna bring the math back to your students, but why is my computer beeping? But you could bring back the fact that, you know, there's computer science, there's dynamical systems, there's mathematics going on, and all of this is playing a role in a biological experience. So look, I'm just saying, like, look at all of the different fields of study that are coming together for this talk. Again, not necessarily that the math itself, the matrix algebra, the linear algebra, the dynamical systems are gonna come back to your students, but it's, hey, this PhD student is working on this project and it's computer science, it's math, it's bio, it's all of these things rolled into one. Again, just reminding our kids that you go into a STEM field, you're not just a biologist, you're not just a chemist. You see what I'm saying? And I think that's super important to remember. And that's always something I'm struggling with my freshmen to explain it to them.
I'd like to comment on that. When I first entered undergrad, when I was in high school, I never wanted to do math. I was good at it for most of my pre-college career, but math was not what I wanted to do. I was originally planning to do engineering for a long time, and then I failed out of the first college I went to, and I went back to community college, and then I decided I wanted to do chemistry, but I didn't get into my undergraduate school for chemistry. I got in for physics, and then I decided I didn't like physics, and I switched to computer science, and then I decided I remember being good at math. It's been a little while since I've taken a math class. Maybe I'll go back to that. And then I was doing computer science and math, and then I finally just finished with just applied math. So I never really thought I would end up here either. I'm sure a lot of your students don't either. But pretty much no matter any of those fields I was going to go into, mathematics in some form was going to be part of it. Whether it's like the logic of the computer science or all the really complicated stuff that physicists do, I didn't think this was going to be where I ended up, but it always ended up being useful.
I just noticed your acknowledgement of RIT's grant writing boot camp. What was that?
I was funded to work on this last summer from a grant from them. And my advisor for this project, Laura, is up top.
Laura, that's not Neil Harris, right?
It's not what?
Neil Harris, no, that's, who's the boot camp? David Bond, right?
Yeah, it was through the provost office, so I think they have an annual, it's just internal funding, so you can apply for.
Yeah.
To get the project going.
So that was just thanking the people who paid me to do this. Indirectly.
Any other questions?
What
Okay.
made you come back after failing? That's a really hard thing to do.
It's hard. So I took AP Calculus in high school, and this is kind of a long story, but I took AP Calculus in high school, and I got a 4 on my exam. And because I got a 4 on my exam, I received an email from the University of Edinburgh in Scotland to apply. So I figured, why not? So I went over there for a year, and I was really depressed, and I had a terrible time and failed out. So then I came back, and it was kind of I need to get out of the house, I'm going to go back to community college thing.
Thank you, that's amazing.
I mean, I failed pre-calculus in high school, probably because I wasn't the best student back when, but you know. Okay, so, thank you, Chris.
Thank you.
I
Thank you,
wish you luck
everybody.
in your program. It's one of the many wonderful projects that's going on with our PhD students right now in our very new PhD program, which we are all very excited about. So what we are gonna do now, and actually that ended with perfect timing because we have to take a walk, okay? And we are gonna go over to the Magic Center for a tour. Please do join us. We will, be meeting with J. Allen Jackson over there, and he will be chatting with us about all of the different things that are possible at the Magic Center, and it is very student driven, and it's their place to be creative in a number of different ways, and it is brand new, so I really suggest you join us.
Are we coming back?
You may come back, yes. I am leaving all my stuff, if that's what you're asking. I am not carrying a thing but my phone and my keys.
That's what we're asking.
Yep, leave your stuff. And I think what we will